So sulfuric acid is H2SO4. Potassium hydroxide is KOH, positive 1, negative 1. So that is going to form what? Yep. So it's going to form, first it's going to be our salt, which is going to be what? K2SO4, because remember, potassium's positive 1, sulfate's negative 2. That's going to be aqueous. Okay, we know that's aqueous because all group 1 compounds, if you have a group 1 metal, it's going to be aqueous. Plus water. Okay, now we're putting this as a liquid. Okay, it's new water. Now I'm going to put in parentheses HOH. If you put water as hydrogen hydroxide, that helps us balance easier, right? Okay? But we have to put water as L because it is a new water. It's not old water it's sitting in, okay? Now, what's going to happen, or to balance, we see that I have 2 hydrogens and 1, okay, because we're looking at the HOH. So I'm going to put a 2 here. That changes the hydrogen to 2, and it changes the hydroxide to 2. So I'm going to put a 2 here to balance the hydroxides. Well, notice that balances the potassiums also. Okay. So that's how you would write a neutralization reaction. Y'all have already done these. This was done during the chemical reactions unit. Okay. Now let's look at titrations. Okay. I'm going to skip ahead. I'm going to skip these examples just because we have a titration today, so we need to leave time to do it. So titrations. A titration is a technique that is used to determine the unknown concentration the unknown concentration. Now concentration is measured in molarity, right? Of an acid or a base. A solution of a known molarity, known as a titrant, is added drop by drop to the other solution of an unknown molarity using a burette. Okay? So in the back, if you see those really tall things, those are called burettes. You should know this because, I mean, Unit 1, we labeled them, right? Okay, we're going to show you how to use a burette and what it means. But basically, we know the concentration of the base that's in the burette. We don't know the concentration of the acid. So we're going to use an indicator to see how much base it takes to neutralize a certain amount of acid. Okay? So a neutralization reaction takes place between the acid and base solutions. Now the solution is added until the end point is reached. This is where the indicator used in titration has changed color. Okay, so in our titrations we are using phenol red. In an acid, what color is a phenol red in an acid? Yellow. Okay, what color is phenol red in a base? Pink. Okay. What color is it when it's neutralized? Peach. Okay? Peach. It's called phenol red because the actual solution is red, but it's not red in any acid or a base. Okay. So, when in our titration, when the solution turns a peach color, okay, it has reached the end point. Now, if a correct indicator is used, then the color change can also indicate the equivalence point. Okay, because that's the whole point, is we're trying to get to the equivalence point. The equivalence point is where the hydrogen ion concentration is completely neutralized by the hydroxide ion concentration. So, the concentration of hydrogen ions and the concentration of hydroxide ions are the same. That is the equivalence point. Okay? Now, if we're doing a strong acid, strong base neutralization, the equivalence point is going to be at a pH of 7. That is the pH that our phenol red turns peach. Y'all follow? So our phenol red turns peach at a pH of 7. When the phenol red turns peach, that tells us that the hydrogen ion and the hydroxide ion concentrations are equal. Okay? Now, here's the setup for a titration. So here in our burette, we have a base of a known concentration. So in our titration lab, we're using sodium hydroxide. We know the concentration of the sodium hydroxide we are using. Okay? In the Erlenmeyer flask, we have the acid of an unknown concentration. We don't know the concentration of the sulfuric acid we're using. Now, we also have phenol red indicator. Okay, we also have phenol red indicator in our solution, so our acid should be yellow. Okay? Now, what's going to happen is we're going to turn this stopcock. So the stopcock, when it is perpendicular to the burette, y'all know what perpendicular means? Makes a T. When it's perpendicular, that means it's off. Okay? When it's parallel, when you turn it and it's parallel, that means it's on. Okay? So we're going to turn it on, and it's going to drop the base into the acid. Okay? At first, it goes pretty fast, but I'm going to explain to you when to kind of slow it down, okay? Because you don't want to go over, because if you put too much base in the acid, it turns pink, and you don't know where the equivalence point was, okay? And actually, I can show you on this titration curve. This is why. What happens is you start dropping the base. The pH is going to start increasing slightly because we're starting off with a low pH because it's an acid, right? As we keep dropping the base, the pH is going to slowly increase because we're starting to neutralize those hydrogen ions with hydroxide ions from the base, right? But there comes a point where it starts to increase very quickly, okay? In between that very quick increase is the equivalence point, okay? So when you're starting to see a color change, so with our phenol red, we're drip, drip, dripping. When you start to see a pink cloud in your yellow acid, that's when you need to start slowing down. You'll start to see a pink cloud. That's when you turn the stopcock and you start to swirl your solution. If the pink cloud goes away, it turns back to yellow, drop, 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 slowly. Okay? You'll see a pink cloud again. Swirl it, then it may go away. Drop, swirl it, it goes away. Now, what you're going to start to see is that it's going to start going away slower and slower. Okay? Your solution even may turn to magenta. If your solution turns to magenta, swirl it. You may have to swirl it for a little bit. And it'll either turn back to yellow or it'll turn to peach. Okay? If it turns back to yellow. If it turned to magenta and it turned back to yellow after you swirled it, you only need like one drop left. Okay? You don't want to send this, so that means it's very close to this equivalence point. So like you would literally just do one drop and swirl it, and it's going to turn back to magenta, and y'all are all going to freak out. But then you're going to sit there and swirl it for a couple minutes, and then it should turn to peach, hopefully. Okay? One drop can throw a titration off, and this is why. Because there's such a steep change in pH. And in between that change is the equivalence point. Titrations are very tedious. Very tedious. So you have to be very precise when you're dropping these. Okay? Now, not all titrations have an equivalence point of 7. This is because some of the ionic salts that are produced in neutralization have their own pH value, which can influence the pH of the equivalence point. Okay, so this happens when there is a strong and weak. Okay, strong acid, weak base, strong base, weak acid titration. So today we're doing strong acid, strong base titration. Our equivalence point is at 7. If you did a weak acid, strong base titration, your equivalence point is going to be at a higher pH. Okay? Your equivalence point is the higher pH. Now, the equivalence point is where the hydrogen ion and the hydroxide ion concentration are the same, correct? If I'm using a weak acid, I'm going to have a lot less hydrogen ion concentration, right? Because it's not completely dissociated. I'm not going to have a lot of hydrogen ions to titrate out. Okay, so our equivalence point is going to be higher because I'm using a strong base. Now, if you were using a strong acid, weak base, your equivalence point is going to be lower. I'm using a strong acid and a weak base. It's got a lot less hydroxide ions. Okay? The salt that's made from these, because I'm using a strong base, the salt that is made from a weak acid strong base is going to have a high pH. Okay? If I'm using a strong acid weak base, my pH for the salt is going to be lower because I'm using a strong acid. Do y'all follow? Okay. So whatever the strong is, that's going to be what the pH for the equivalence point is going to be. Just about. Now, even crazier, polyprotic acids have multiple equivalence points. One for each hydrogen ion that dissociates off the acid. As each hydrogen ion is neutralized by hydroxide from the base, a sharp change in pH will occur, and eventually all the hydrogen ions will be dissociated. So they dissociate one at a time. Try finding the pH of each one of these. It's difficult. Because the first pH is easy. If it's a strong acid, polyprotic, then the first pH is easy to find. But then the second and the third, you have to do all these different fancy ice tables and all this other stuff. It's really tedious. It's difficult. But, I mean, you'll be doing that in AP Chem. Okay, because we're not making you try to find the pH of a weak acid or base in advanced chem. You're welcome. Like I said, it's a lot of work. So once the titration is complete, there's more than one way to calculate molarity. We can use stoichiometry to make the calculation. Okay, so these examples, this is after my titration is complete. So basically, let me go back to this. What happened was I titrated, I dripped this base, and it turned peach. Yay. What you did is, you say you recorded the starting volume as, 10 milliliters, and our ending volume is 35 milliliters. Now notice, why is it 10 on top and 35 at the bottom? Think way back to Unit 1 with burettes. It's reversed. Burettes are reversed, right? So when you go back there, the top of your burette is going to be 1. The bottom's going to be 50 because it's how much is dispensed. So pay attention to that. Okay? So if I started at 10 and then at the end of my titration I ended up at 35, okay? How much base did I use? 25 milliliters. Is that right? Yeah. 25 milliliters. Wow, math. Early in the morning. So I used 25 milliliters of my base to titrate my acid. I can take my 25 milliliters, the molarity of my base, and the volume of acid that I measured out at the beginning to find the molarity of the acid. Okay? So these problems are after titration has occurred. So it says if 45.8 milliliters of a 0.5 molar solution of calcium hydroxide is required to titrate 25 milliliters of hydrochloric acid, what is the molarity of the hydrochloric acid solution? Also, write your neutralization equation. Okay? So first, let's write our neutralization equation before we deal with the numbers. We have calcium hydroxide. Oh, look, it gave us the formulas. So nice. Calcium hydroxide plus hydrochloric acid. Notice how I'll write my, my states. Very cutesy, very demure. Okay. Now, it's going to form what? Calcium chloride, what's the formula? CaCl2, that's aqueous, plus water, H2O, which is a liquid. And again, you can write it as HOH to help balance. Okay. So I see I have 2 hydroxides here, but here I only have 1. So I'm going to put a 2 in front of my water. That changes the hydrogen, so I'm going to put a 2 here. Okay, and look, that balances out the chlorines. Perfect. Now, it says if 45.8 milliliters of a 0.5 molar solution of calcium hydroxide is required to titrate 25 milliliters of hydrochloric acid. So let me kind of show you what's going on. Here's our burette. Okay, here's our acid. Notice, oof, my Erlenmeyer flask is rough. But basically, in my acid, it is 25 milliliters of hydrochloric acid. Okay? I used 45.8 milliliters of 0.5 molar calcium hydroxide to titrate that 25 milliliters of hydrochloric acid. Okay? So what I can do is I can start with the amount I needed, or the amounts used to titrate my hydrochloric acid to find my molarity. So we're going to be doing some stoichiometry. Now, you may have done this differently in Miss Cyrus's class, but I like to do my conversions kind of all at once and then do the molarity calculation. Okay, so what our first conversion is going to be, we're trying to get from 45.8 milliliters of calcium hydroxide to moles of hydrochloric acid, because then I can use the moles of hydrochloric acid and the volume of hydrochloric acid to calculate molarity. Do y'all follow? Okay, so let's start with 45.8 milliliters of calcium hydroxide. Okay, now we can use molarity as a conversion factor, right? Because it's moles per liter. That's how many moles are in 1 liter. So I can use that conversion to go from liters of calcium hydroxide to moles of calcium hydroxide. Well, before I can go from liters to moles, I need to go from milliliters to liters, correct? Okay. So I'm just going to do it the old-fashioned way. 1,000 milliliters of calcium hydroxide and 1 liter of calcium hydroxide. Okay. Now that's my first conversion. And again, I like to do all of my stoichiometry together. Makes things neat. Okay. That gets me to liters. So my next conversion is going to be what? Liters to moles, using our molarity. Okay. So in 1 liter of calcium hydroxide, how many moles? 0.500 moles of calcium hydroxide. Okay. That's the beauty of molarity. It can go from volume of a solution to moles of a solution. Why didn't I use 22.4? Because isn't 22.4 liters? Why didn't I use that? What is 22.4 used for? It's for gases. Okay? 22.4 is used for gases. We don't have a gas here. We have a solution. Molarity is used for solutions. Okay? Now that gets me to moles. Now my next step is to go from moles of calcium hydroxide to moles of hydrochloric acid. How can I do that? Mole ratio. Okay? Molar ratio. So we're going to go from calcium hydroxide. 1 mole of calcium hydroxide, according to my balance equation, what's going to go on top? 2 moles of hydrochloric acid. Okay? Now, that gets me to moles of hydrochloric acid. So when I calculate that, I get 0.0458 moles of HCl. Okay? Now, I can use that to calculate my molarity of hydrochloric acid. Okay, so I got my moles, which is 0.0458 moles of HCl. Okay? But, what is my volume of HCl? 25 milliliters. So I'm going to need to do another conversion. So I'm going to go down here, do a little conversion. Okay, and that's going to give me 0.025 liters. Now, how many sig figs should my answer have? 3. 3 sig figs, 3 sig figs, 3 sig figs. So what would my answer be? 1.83. 1.83 molar hydrochloric acid. Woohoo! Notice how much stuff from this year we used in this one question. We used so much, right? In this one question. Okay? So, this is a titration problem. Now, what we're doing today in the titration lab is what we're trying to find is this, essentially. Okay? How much base is it going to take to titrate our sulfuric acid? We are trying to find this number. Next class, it's next class, we're going to be doing calculations using that number. Okay, you're doing 3 trials today. So you'll have 3 different volumes, but I mean they should all kind of average out to about the same. Okay, because we're using the same concentration, so you should have about the same volume for each trial. But again, this is your first time doing a titration. We do 3 trials because you may not get the first trial. That's okay. Okay? Your grade is not based off if you get the titration correct, if you get a pH solution. Now, it's great if you get a pH solution. Everybody else has been able to. So your group should, at least by the 3rd trial, get one. Okay? And I'll guide you through it. But the whole point of this lab today is to get this number. Because then if we have this number, then we can calculate the molarity of our sulfuric acid. Okay?